Hello, and welcome to the last video in the series where I explain my Houdini system. In this video I will be going over the tensor field, which was my idea for how to generate a city. In this case we're going to start off with the first iteration of it. So in this first iteration I take the terrain as an input, so here we have our terrain, which you should recognize from the earlier video, and in here I again make a slope map. This time it is visualized by a different color. I use grayscale instead of the black body I used previously, but here we go. We again have our slope value. So this first version actually was it didn't work as I wanted it to. I took the wrong steps and it turned out badly. So what I do here is using the group node, which is a node that can group points together based on certain parameters. So here I basically say, okay, the slope value has to be between these two values, 0.038 and 0.1 in this case, and the height has to be above a certain value, so it has to be above the river section, and the height also has to be below the top, so I don't want to get this point, for instance. So using that group I delete the rest of the geometry, which leaves me with all these points. So as you can see here, I'm left with all these points that I now want to turn into a tensor field. Now I tried a lot of things to turn these back into curves. I had written a piece of code that could aim the normals of the target geometry, or the aiming geometry in this case. So that would be this geometry. That would be the aiming geometry. And I've made a piece of code that could aim the normals of these at their closest point on the target geometry, which is this. And with that information I wanted to make them follow the curves. Now the problem was with this is that I couldn't just make them target at points, at random points. They needed to have an order. Thinking back, I could have done certain things to do this, but at the time I didn't think of that, and I got really stuck on this idea to making these points into curves again. And I tried a lot of things, adding things, trying to add them, but every option I tried kind of didn't work. Nothing turned out right. And after a long while, actually, I got the suggestion from Fernando that I should use Voronoi. Now, that was kind of unclear to me what I should do with that, and he then explained, well, right now you're deleting a lot of information, so I'm only keeping these points, and I should do it the other way around. I should keep the areas that are valuable or usable for the system. So that gave me an idea, with which I moved on to the second iteration of the curve extraction system, but really the tensor field testing. So this is the whole system. It's become quite cluttered, but let's just start off at the top. So still the same steps, turning the geometry into a slope map, and again deleting a bunch of points, but this time I'm keeping the flat areas. So as you can see here, I already have a lot more to work with, and using only one more node I actually already have kind of the things I wanted. Now the real problem I had here is that when I turn on my wire shaded, you can see that there's a lot of points in here still, and I didn't want that. So using a grouping node together with a dissolve node, I delete those inner points. Now what a dissolve node does is it looks at a certain group of edges and deletes points very cleanly, also deleting the edges, primitives, everything. It does this very well. I wouldn't have been able to do this with a blast node or a delete node, because that would just delete the whole geometry, destroy it basically. So I again smooth it to kind of give it a nice look, and after some more stuff I basically have my base target curves. Now from these target curves I move into two parts of the system: the edge detection system as well as the tensorfield system. So for now I'll move on to the tensorfield system first, because I find this more interesting than the other parts. So here we go. What I do here is I basically clean up the whole stuff. So you could see that there's a bunch of points with a very small area, as well as points here, and I don't want those. So using a delete node and a measure node, which measures the area of a primitive, and right now if I turn on the primitives you can see that these are just really big primitives. But also primitive number 7, which is basically nothing. It's a primitive that's so small that it cannot even be seen. It has no area, or well, really small area, and I don't want primitives like that. So if the area is 0, I delete it, or below a certain value. So you can see that a bunch of primitives just disappeared, and boom, I only keep the major ones. So looking at my next step, I try to delete that primitive that you just saw there, so this one. I try to delete that by looking at the neighbor points. So it counts, it looks at a point and it looks how many neighbors that point has, and it gives it a number, for instance 5. Not very common in this case, because it would only have 2 neighbors maximum. But since it's still primitive, they're all connected, so I had to do by area. So this step is basically useless. And if I skip it, later on nothing will change. So here I kind of sort the points. So the point order is following the z-axis, and I add some normals to them. So if I turn on the normals, you can see all the geometry now has a blue outline, and these are the normals pointing along them. Using this, I didn't want this section to be here, so using this option I delete it. So you can see I just deleted this because the normals were pointing in a certain way, and afterwards I use this attribute. So this is the count attribute, and what it basically does is it determines the direction of the curve. So when we go here and look at some points here, this point will always have a lower count attribute than this one, and this one will always have a higher one than these two. Using this I can determine the direction of the curve, and with that I can determine the direction the normals should be pointing. So this is basically the problem I couldn't solve in the previous system. And I'm very proud that I was able to solve it now, because it did take me a long while. So in here I was also able to take the geometry, both the normal geometry, my basic testing geometry, and my target curves, and I find the closest point for the aiming geometry on the target geometry. So the geometry you see here, this terrain, looks for the closest point on these curves. Now there are curves, there's still a polygon in between them, but I'm viewing them as curves right now. So it's looking at the closest point on there, and then using a simple formula as well as that count attribute I made earlier, I make the normals. So in here you can see there's no normals. They're all, well, they are there, but they're all pointing up, or at least outwards from the geometry. And here they're suddenly following the terrain. So you can see it a bit better here. If I look from atop and turn off the wire shades, you can see that it's in fact following the terrain. Now this was also the point where Fernando's idea came into place. Use Voronoi. When we look at the geometry spreadsheet, you can see that there is 9,999 points, and there's a lot of primitives, 9,800, which is a lot to run over. So using Voronoi, I basically go through the same process. I take the input geometry, delete the sections that are too low, make sure I only have the outlines, and I use a Voronoi fracture on them, which gives me this. This is basically a grid, but instead of having 4 neighbors, each point has only 3 neighbors, which is very useful later on. I basically transfer the normals between them, so this grid with its normals and this Voronoi grid without, well, with basic normals basically. And here you can see the Voronoi grid now has the normals on it. So if we turn off the wire shading, you can see the normals are pointing in the right way. Let me actually make those normals a bit bigger so you can see it a bit better. So here we go. You can see now, right now, the curves really become apparent. You can really see how the normals are pointing along, and there's still some artifacts like in here or here, but looking at the whole picture, these are not too important because I managed to smooth them out later on. Now with these normals, with this tensor field, as I call it, I am able to make roads. So the normals are become quite important from here on. So in this node, I basically mess up the normals. So the points on the outside, especially the river and everything, is really messed up. And I do this so I can use this. Now what just happened is I looked at the normals. Let's for instance look at this point. Now this point is going to look at its 3 neighbors, so that's 1, 2, 3. It looks at its neighbors and it looks and thinks, okay, how big is the change between the normals? Now between these two, this one and this one, the change isn't very high, but with this one it is really high. And therefore it keeps itself. Now if the change is too low, for instance in this section, this point, all its surrounding neighbors have a very low change in normals. So I delete it. And with that, I get this. That's why why I messed up the normals here on the edges, so that I would definitely keep these edges. So yeah, right now I basically have some base geometry for making my road curves. It's very cluttered, as you can see, but it's something to work from. So what I first do is I change all the primitives, all the polygons you saw, I put points on them. Now I had a problem with this earlier, that because there's still a lot of unused primitives. So when I go to the primitive section here and I click this, you can see I use the area node or the measure node set on area once again, and you can see that some primitives have 0 as an area. So number 1661 has 0 area. This is because I have deleted the points that are on that primitive, but the primitive itself doesn't delete itself. So here I basically do that. I say if the area is 0, you delete yourself. With this section especially, I was getting a lot of problems because this makes points per primitive. Now if there is a primitive that technically seen exists, but it doesn't have an area, it doesn't have a location, it doesn't have everything, it's making a point that is redundant. So if I turn this off, you can see the amount of points greatly increases. So let's just kind of flicker this, so you can see a bunch of points are left over, unnecessary. Now I don't want this, because this is a lot better to work from, because these are already detailing a lot more what I want. Now using this information, I use the connect adjacent pieces node, which basically makes lines between points. And as you can see here, the road curves are already kind of coming to place. Now, using a bit of scripting, I basically delete points that don't have enough neighbors. So let's just turn the points on here. You can see there's a bunch of floating points. So here there's some, here there's some, I think up here there were some as well. Some hidden here, down here as well, and I delete those because they don't have neighbors. Now this is basically cleaning up the geometry, and here I smooth them. So right now they're looking much more funky, and this kind of hexagrid I had here, so when I go before this, you can see this is all very cluttered, but here it becomes much more, well, smooth, because it's smoothed. This is again a section I got stuck on, because I couldn't figure out how to connect everything, how to make everything look good, how to connect everything correctly. Now, on suggestion from Feike, I used something very simple. I used a fuse node, but it is set to a very high distance. So that means that the search radius around the point is very high. Now again, cleaning up the geometry, and again, a fuse node to clean up those pesky points, because sometimes there's 2 points in one space and you don't want that, obviously. And after some more work, I connect everything else. So here I basically add another counter attribute, so I look at the neighbors again. So this point will have no neighbors, and therefore it needs to be connected. So here I'm basically closing all points. Now this point here, this line here to be specific, it goes over the river section, and I don't want that. Right now that doesn't matter though, because it gets deleted later. Now this doesn't fall within the tensorfield section, but I make some subroads, and afterwards, as you can see by the way, the river, the thing that went over the river gets deleted. And kind of showcasing the roads a bit more, I add the bridges as well, which I'll showcase later on. And here I have everything together, so let's turn those points off. Let's turn the wires off, and as you can see, it looks pretty decent. I found at least. So quite proud of that. But now, how did I make these bridges? So let's go up once more and go back to our target curves. Now it starts off pretty similar. I delete points that have too low area. So we went from having those curves here to, well, not having them here. And again, using Voronoi, I have to turn back on the shaders or the wires. So again, I make a Voronoi diagram out of it, but I also keep the points. And I use again the connected adjacent pieces, and using that I find the neighbors, or at least the edges of the geometry. So as you can see here, I have those points here. I do this by looking at the amount of neighbors a point has, because a Voronoi diagram, each point will always have 3 neighbors. If it doesn't have a neighbor, that means it's either on an edge or something else happened. Now as you can see here, that does not always work, because when I turn this on, this point still has 3 neighbors. This one might not. This one's 2 neighbors. This is on an edge definitely, but these other points still have 3 neighbors. And what I do for that is I look at this one. So these are the center points of the Voronoi. So when I turn this on and turn the Voronoi on, you can see that each cell has these points as their center. Now, what a Voronoi cell always has is that, it's always surrounded by 7 polygons. So you can see, let's select, let's select this one, and you can see that it has 1, 2, 3, 4, 5, 6. 6 surrounding ones. The edges though only have 4 usually, so again let's select it, and 1, 2, 3, 4. In some cases they are very close and it makes it appear like there's 5, such as in this case. So we've got 1, 2, 3, 4, 5. But these are kind of exceptions. So as you see in here, this is also a place where it kind of fails. So what I do is I look at these points and I look at how many neighbors they have, and if that is 3 or 4, that means that it's fine, that it's definitely an edge point. Now to kind of visualize this, I transfer it on top of the Voronoi diagram. So here you've got a much more crisp depiction of where the edges are. Of course, we know where the edges are, but the Houdini system doesn't, obviously. So here I'm kind of showcasing that the system does actually work. This was more for having myself being able to see that it works. It is flawed, as you can see, because here there are still some primitives that are left black, even though they are on an edge. But that's because I'm again using the connect adjacent pieces node, and that connects points based on search radius. So this one is definitely on an edge, but it's also connecting to this primitive because it is within the search radius. So that's the problem I was having there, which I have not found a solution for yet. Although I take the points, not the primitives, and I turn them into normal points. Now I think I still have this turned on somewhere. No, I definitely do not. Okay. So I only have the red points right now. They're just floating around here. I create an attribute, which is called connected. There it goes. So this is going to be my identifier. And here I connect everything and delete all the unnecessary points. Whoops. So all the unnecessary points get deleted, and I am left with a lot of bridge curves. These shouldn't be here because there's a lot of them, but it's a start. So from here I again loop over the primitives, look if their length is too long. If it is, I delete it. Whoops. And the last script, which is here, I pick out a couple of them. I do that by setting a dominance for each section of it. So going back to this, I basically say you're either a 1 or a 0. I do that for everyone. This is not rule-based. It's just arbitrary. Each primitive or each line segment will look around itself and say, okay, I'm going to look at all my neighboring primitives. If one is too close, I'm going to look at my own dominance and its dominance. So if my dominance is 0, then I will delete myself. If it's the other way around, I'll delete the other primitive. That way I'm only left with these primitives or lines, which I later on merge with the roads, and I fuse them so they kind of work together. And then we're back at what I just showed. So this was the last video of my system, the tensorfield. Overall, I would say the project came along pretty well. I would have liked it to be a bit more controlled, especially the tensorfield system. The roads are looking pretty decent, but they definitely could have been better. So that's something for the future. I would definitely come back to this project and fix these things later. So again, thank you for watching, and I'll see you at the panels.